5.10 Introduction to Optimization. Optimize. To make the best or most effective use of a situation or resource. Strategies for solving optimization problems. 1. Draw a picture, if applicable, and identify known and unknown quantities. 2. Write an equation or a model that will be optimized. 3. Write your equation in terms of a single variable. 4. Determine the desired max or min value with calculus techniques. 5. Determine the domain or endpoints of your equation to verify if the endpoints represent a max or a min. 1. Find two numbers whose sum is 30 and whose product is as large as possible. So product, we'll label product P, and that is equal to x times y. And that'll be our two numbers. We also know that x plus y equals 30. We can solve for our y value right here by moving x on the other side, and this would be y equals 30 minus x. Now that we know what y is worth, we can plug that into our P equation. So it'll be P equals x multiplied by 30 minus x. Factor that out, or multiply that out, be 30x minus x squared. And this will be the equation we use to find the answer. Number 2, what point in the graph y equals square root of x is closest to 5, 0? So let's say, just guessing, this is the closest point, and we want to find the distance between 5, 0 to this point right here. Now, to find the distance, we have to use the distance formula, which is d equals square root of x2 minus x1 squared plus y2 minus y1 squared. Now we just plug in our points. This point, since right here it says y equals, on the graph y equals square root of x, we could say that this point is equal to x square root of x. So now that we have our points, we can plug it in. So it's square root of x minus 5 squared plus square root of x minus 0 squared. Simplify this out. The equation we're going to use is x minus 5 squared plus x. 3. Mr. Kelly needs to make an open top box to store all his magic cards. He has a piece of cardboard that is 14 by 30 inches. To do this, Mr. Kelly cuts out squares of equal size from the four corners so the four sides can be bent upwards. What size should the squares be in order to create a box with the largest possible volume? First, we draw a square. Since he's cutting out the corners to bend it upwards, we're going to draw what he cuts out. And we don't know what he's trying to cut out, so we'll just label each of them X for now. And we also know that this is 30 inches and this is 14 inches. Now the formula for volume, we know that volume equals length times width times height. Now we could plug in some values into our equation. We know that the length is 30, but we have to account for the length that we lose right here. So 30, we lose x and x right here. 30 minus 2x multiplied by the width, this is 14 minus 2x. And then multiplied by height, which is going to be this folded up. So this is just x. Then we multiply this out, and the formula we're going to use is volume equals 420x minus 88x squared plus 4x cubed. 4. Two towers are 30 feet apart. One is 12 feet high and the other is 28 feet high. There's a stake in the ground between the towers. The top of each tower has a wire tied to it that connects to the stake on the ground. Where should the stake be placed to use the least amount of wire? First, we're going to draw our two towers. This is 28. This is 12. Let's draw a point in the middle where the stake is going to be connected to. These are our wires. Call this wire 1 and call this wire 2. We'll call this distance in between the wire and the second tower x. And we'll call this 30 minus x, since the total is 30. Now, we know that the total wire length will be W1 plus W2. And this is just our distance problem, or not our distance problem, the Pythagorean theorem. So wire 1, this is just, we have to find the hypotenuse. So this is equal to the square root of 28 squared plus 30 minus x squared plus the square root of 12 squared plus x squared. And we're going to use this formula to find where the stake should be to use the least amount of wire.